Well, everything is on record now, so I've started the recorder.
So what do I say?
It's like a court, right? When they court, when it's recorded on the.
I was born skinny. I can dislike anybody I want.
Absolutely.
Or even not even dislike. For some reason, I was born skinny.
Or you can start with a statement, I dislike everybody except.
That I'm gonna have to take
just
421 and
except
431 in spring, and that's gonna be. Well, I have no other choice.
So let's go ahead and get started. Yes, I can see the class is definitely getting a little bit thinner now. Maybe 50% of what should be here, and that's why I'm going to take roll today, just to see who is here and who's not. Well, one purpose of this is just to collect statistics, to see whether being here in class has any correlation with getting a reasonable grade out of this class. Okay, I think few people can probably still get like a really good grade out of this class just by watching the YouTube videos and not having to ask questions whatsoever. But I think the percentages tend to be a little bit low for this kind of class. For some other classes, I can see the percentage can be pretty high just by watching a lecture, especially classes that can be turned online really easily. I would never teach this class online. I mean, if they ask me to teach it online, I would just teach it on a Saturday or something. We do have classes on Saturdays, in case you do not know. Okay, so what we'll do today is to finish up the program that I started on Tuesday, and then we'll move on and talk about the call frame. Okay, so the call frame is one of the important parts. And we'll also schedule our second exam. Okay, the second exam is going to be scheduled 1 week from next Tuesday. So next Tuesday we'll have a practice exam. So we'll talk about the questions and the kind of things that can be asked in the second exam. And then 1 week after that will be the actual exam number 2. So this way you have time to prepare for that. And I know the second exam is pretty close to the final exam, but we'll have it anyway. And there will still be material left over, for the final exam, because we will have, some additional stuff for the final exam too. So are there any questions about the stack, the call instruction? Yep, go ahead.
Sorry, it's about the final. Is it cumulative?
The final exam is cumulative, but it has a focus on the stuff that we talk about after the second exam, or actually starting from now. So the second exam will only talk about stuff up to the push pop instruction and the call return, but it won't cover anything about parameters on the stack. Okay, so everything that some of the stuff that we talk about today will be in the exam, but some will not be in the second exam.
Okay. I think that's also something cool. Like, we have access to our computers, or should we start printing everything out right now? Well, I don't know. We have access to computers.
Probably not. So it'll be pretty much the same as the first exam. And I'll try to ask questions in a way where if you understand the concept, you will still be okay. So you don't really need to run the program in GDB to find the answer. A lot of the stuff, in the practice exam, a lot of that, you can actually do it on a piece of paper too. Yeah, if you have access to if the class can take the exam on actual computers, I would actually have to change the type of question. So instead of, identifying what is wrong with this program, you might actually have to write, a subroutine to do blah, blah, blah. So it'd be kind of like a miniature homework assignment in that case. All right, so getting back to the program that we were working on Tuesday. So let me go back to that folder first. So it's 2013, 04, 09, 2010. It's a print text and oops. Okay, so we got the C version. Oh. So we have the C version of print hexadecimal, and we have the recursive one, and the recursive one is the one that I will implement in this case. And this is before we even talk about how to pass parameters and stuff like this, stuff like that. So as I go over this particular program, we'll go over some of the concepts that are introduced in the new topic. that when we talk about the call frame. Okay. All right. So what we'll do is we'll just go ahead and I will go ahead and copy this file from the .c to a .s file, and then go to the .s file, and then comment out things, delete things that I really don't need, such as stuff all the way up to here, and keep the subroutine because that's what I'm implementing. I can get rid of main, for the time being too, so I can just kind of focus on the subroutine itself. So I will substitute everything at the beginning of each line to the pound sign followed by a space. So this way, they're all commented out. Okay. So before we talk about subroutines, things are fairly easy to do because we just have quote-unquote global variables to take care of everything. But now that we have a subroutine, the first thing we see when we see a subroutine like this is how do we pass a parameter into the subroutine? In other words, how do we pass the number that we are supposed to print in hexadecimal, into the subroutine? That's really the question. Well, we do have several ways to pass, information into a subroutine. The first one is to have static global, quote-unquote, global variables. In other words, you put the number that you're supposed to print in hexadecimal into a quote-unquote global variable, using the blah 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 dot and 0 type of construct to allocate 4 bytes. And because that is natively a global label, so that means throughout your entire program, you can just use that as a mechanism to pass information. You can also use registers. In other words, you can just say, by convention, by my own convention, register EAX is going to be the number that I want to convert and print in hexadecimal when I call this subroutine, which is fine. Okay, so that's not a bad way to do it either. I would use registers, because it's more efficient for one thing, and you do not need to define something that is global either when you use registers to pass information in. There's only one big downside to this particular approach. We only have so many registers. Okay, so when you run out of registers, then you still have to go to some other method of passing parameters. But for this time, we'll just go ahead and make that assumption.
Can you pass memory addresses through a register?
Yes, you can. So you can pass a struct if you want to. But a struct is a little bit hard to implement in assembly language because you still need to allocate the space that your register is pointing to. Okay. So it still kind of gets back into the same problem that we had to begin with. So until we talk about the call frame, there's no easy or nice solution to this particular problem. But for now, we'll just use a register in this case. So we'll say, parameter n is assumed to be in register EAX when this subroutine is called. Okay. So that's a convention that I have to, remind myself, because that's the way it is. CH, interestingly, I may or may not need a place to store CH, so I can probably use another register for CH. So right now, I'm not too concerned about CH. So I'll just kind of go ahead and start with this logic here. And I'll go through the step-by-step process to basically say, okay, I can turn this into a non-structured code to say that if n does not equal to 0, go to the else label, okay? And the else label is going to be defined here, just like that. At the end of the then branch, we have to do an unconditional branch to the end if label, because otherwise we'll be passing through the other part. And the end if label should be defined here at the end of the entire conditional statement. So are we doing okay so far? Because I'm just laying out the general overall structure of the outer conditional statement. And I'll do the same thing with the inner ones too. And since I'm using this process, I might as well just go ahead and implement the actual instruction here, because I have it boiled down to a point where I can actually implement it. Because right now, if you look at the line right above the cursor, it says if n does not equal to 0, go to else. I think I can do that with one compare instruction combined with one conditional branch instruction. Okay, are you guys kind of convinced? Okay. And this one, because it's just testing for the equality to 0, the comparison is just compare long, because n is a uint32, so that means it needs to be stored in the entire EAX. So compare long is the right one to use. we're comparing 0 to EAX because n is supposed to be in EAX right now. And jump, if not 0, to else. So that's how we'll implement, the conditional part of the outer conditional statement. So now the outer conditional statement is all done. So the next thing we have to do is to figure out, how to perform, writing 0 to the screen, the ASCII code of 0 to standard out in this case. In the C version of this code, we do have a local variable called 0, because otherwise I cannot pass the address of the byte that contains the ASCII code of 0. But when you do this in assembly, there are shortcuts to this, okay? Because basically you have ways to allocate memory on the fly, get the address to it without having to name that particular place. So I'll kind of talk about how to do that here. Several things we have to do anyway, moving forward into EAX to basically indicate that this is a write operation. You have to do that. Moving 1 into EBX to mean that you are using standard out as the output file, you still have to do that. Moving a 1 into EDX, which is the last one, the last parameter, which indicates that we are printing only one single character, you still have to do that. So the question now is, but how do we deal with, passing the address of the byte that we want to print, which is supposed to be the ASCII code of 0, to register ECX? That remains to be the only thing that we have to figure out how to do. Let's look at this instruction here and tell me what you think of it. Push W, I cannot push byte. There's no such opcode for push byte. So the smallest thing I can use to push onto the stack is a word. So I will push the ASCII code of 0, and then I'll move ESP into ECX. Oops, I said ECX, but I typed EDX. Here we go. All right, so look at these two instructions. Let me turn on the line number so we can actually talk about which line here. So if you take a look at line 16 and line 17, together they will accomplish both, putting the ASCII code into some memory location and making ECX a pointer to that location. The first instruction on line 16 is pushing the ASCII code of 0. The ASCII code of 0 is 30 in hexadecimal, so when you push it as a word, it becomes 0030 in hexadecimal. And I'm pushing that on the stack. Now when you push something on the stack, your stack pointer is decreased, and then it will allocate the 2 bytes in this case to store 00 to the high address and 30 to the low byte. And then ESP points to the very last thing that you pushed. And the very last thing that we push is the ASCII code of 0 itself. So that's why the second instruction, or on line 17, I can just copy the stack pointer to ECX, and now ECX is also pointing to the very same location where the ASCII code of 0 is located. Is that making any sense? So this is kind of like a weird combination of things that we have already talked about. Okay, we talked about how the stack is used in a push instruction, and we also talked about how to use the system call to write certain bytes into the output stream. And so we're just combining those two concepts with these two instructions. Are there any questions about line 16 and line 17? Because that's the really odd one here. That it's kind of like a new use of existing instructions that we've done. Yep, go ahead.
So wait, so why are you pushing 16 bits instead of 8?
Because there's no such instruction to push 8 bits on the stack. Okay. So the smallest quantity I can push is 16, but that's okay, because out of the 2 bytes, I'm just using the least significant byte. The most significant byte is just wasting space on the stack. Yeah.
Aren't you changing the value of 10 because it's going to be
I don't need. Oh, okay.
When you
That's
move
right.
forward.
Okay. So we'll address that problem next. Okay. Very good. Okay. So now we can use the int, the software interrupt instruction, int $0x80 to actually ask the operating system to perform the operation. Yep.
Do we need to pop that 0 back off after the move?
Okay, well, that's a good question. Okay, so we'll address that too. So there are a few things that are still dangling, okay? But right now I'm just concerned about, okay, am I specifying the right parameters to system surface number 4? Okay, so that part seems to be right. So you guys are perfectly correct, okay? So you're correct that EAX is our n, so we need that back at some point. And then you are also right that we have something on the stack, and the stack is now not balanced after the system call. So we'll address that now. Okay. So the first thing first, okay? Do we need EAX back when we are at this point? In other words, if you look at the C code, afterwards, it's a big, long, huge, if statement, but there's nothing to execute after this that relies on n anymore. So technically speaking, I don't need to preserve n at this point, but it's probably a good idea to just to preserve it, just in case we add, additional logic that depends on n later on. So what is the quickest way to preserve the value of EAX? Obviously, I have to do it right before I destroy the value of EAX here.
Push it on the stack.
You can push it on the stack. Very good. So we say push L, EAX. So now EAX is saved on the stack. And then there's another push L, push W instruction here to push the ASCII code of 0 onto the stack. So by the time we get back from the system call, how many bytes are on the stack? That is done by line 13 to line 19.
6.
There are 6 bytes on the stack. Do we need to pop those 2 bytes back into some place, or do you think it is just useless at this point? The 2 bytes pushed by the push W instruction.
They're useless.
They're not useful, right? Because all they're doing is really just for the printing purposes. So now that the system call is completed, I really don't need those 2 bytes anywhere anymore. So instead of popping it into a register, which it really doesn't do me any good, one quick way to basically quote unquote deallocate those 2 bytes is to add 2 to the stack pointer. That's all we need to do. In other words, I'm just moving the bookmark through memory, and to say that, oh, you know what, these 2 bytes, we don't need that anymore, without actually copying those 2 bytes to any particular place. Are we doing okay so far, with balancing the push W in this case? So we now still have, go ahead.
That's pushing 2 bytes, but there's 3 on the, or 6 on the.
There are 6, so we need one more instruction to balance it.
Okay.
So the other instruction to balance it is to pop back into EAX, because we were preserving n on the stack here. So preserve n on the stack. So down here, what we are doing is we are restore n from the stack. So this is a quick and easy way to make use of the push and pop instructions, so that if you know that you need to preserve the values inside a register, but you need to use that particular register anyway, you can just push it first, do whatever you need to clobber the register. When you're all done, hop the register back to restore its old value, and you're all good to go again. Okay. And this is a really, really common practice in assembly language programming, is to utilize the stack to save and restore values of registers. When you're only doing it locally within, I would say, 20 lines or so, it's pretty easy to keep track. But if you are pushing and popping, and the push and the pop are spaced out by 30 or 40 lines, that type of program gets pretty hard to track, because the push is so far away from the pop that if you forget to do it, or there's a conditional branch and sometimes you do it and sometimes you don't do it, then you can end up with kind of serious problems, because the stack will not be balanced in the end. All right, so I think that's the then branch. I think that should do it. You know what? I'm going to finish the rest of the program just to test this one here. There's one more thing. At the end of the subroutine, I have to make sure that I have a return statement, because otherwise it's not going to come back, or it will just kind of fall through and move into the main program itself. So we'll go ahead and put a dot text here, dot global underscore start, and then go to here and label underscore start here. I'll just go ahead and test, can I print 0, successfully? Okay, so I'm putting 0 into EAX, call, I forgot to give it a name, so I got to give the subroutine a name here. This is too long, recursive underscore pretext. I'll just say pretext here. Give it a label, print X. And then when it returns, it's time to exit the entire program. Move 1 into EAX, move 0 into EBX, and then do a software interrupt. So this is my program up to this point. I think I have written enough code to warrant a quick test to make sure that this part at least is working. Okay.
You left an extra character at the very top.
No, it's a roll over on the line.
Yeah.
At the very top of the.
Well, I'll let the assembler complain about it.
Oh.
Okay.
You're talking about the D.
Well, let's just say that I did make that mistake, because sometimes we do make mistakes, so we want to see what kind of error we'll be getting out when we do that. Well, apparently I did not. Well, if it's a label issue, it won't be reported by the assembler. It will be reported by the linker.
It was just a line wrap.
Oh, okay.
Yeah, there was no line number for it.
So we'll go ahead and link it. Print hex is the executable, and the print hex.o is the object file name. So everything seems to be okay, and it printed just a 0 here. So the program is behaving just fine. This is exactly what it should be doing when I ask it to print to just 0. Okay. So now it's time to implement the else part. Okay, here's the else part. The else part has its own multi-branch conditional statement, because depending on the remainder of the division, I have to go one place or another. So I will probably just implement one branch first, and then if that works, I will implement the other branch as well. But the first thing I have to do is to finish up this whole thing about the division. Okay. So how do we do division in assembly language? Okay. So this is all done by the diff-l instruction. The diff-l instruction is I'll just do a quick comment here. This is also in its very own notes on the website. Okay, how to use the divide instruction. The divide instruction is going to use EDX, EAX combined, as the dividend. Okay, the number to be divided, and then we have to supply the divisor as one operand. After the operation, EAX will be the quotient, and then EDX will be the remainder. That's really just the convention, and it's kind of like the multiply instruction where it only has one single operand, so the use of EAX and EDX that are implied, which makes it not a very nice instruction, because unless you remember all that stuff, if you forget to initialize EDX, for instance, then you end up with a unpredictable upper 32-bit for your dividend. So your division will just go completely crazy because of that. So that reminds me, I need to do something about it, right? So I have to move a 0 into EDX, and I'll just write a comment here, because EDX is bit 32 to 63 of the dividend. This is implied. Okay. So what we are dividing is 16. This is a division by 16. I'm not sure that it will even take this operand. An immediate operand may not work with diff-l. So I'll just go ahead and do the assemble first. Yep, sure enough, it doesn't like it. All right, no problem. We just have to move 16 into a register first before we actually perform the division. So we have to move 16 into a particular register. Just pick one that we haven't used, or is not used in this particular instruction. EBX is fine. Then we'll divide, using EBX as our divisor. Okay. And after the division, we should have the quotient stored in EAX, and then EDX will be the remainder. Okay. So at this point, if this is the very first time I use the diff-l instruction and I was told about how to use it, I would just stop, put a breakpoint here, and make sure that the operation is done correctly. So this is what I'll do, actually here. Okay. Now, if you are writing a particular piece of code and you don't want yourself to forget what was the last place that you were working on, You can always use comments to leave a note here and just say, to do, finish the rest of the branch here. Okay, so the to do is basically, if I turn on syntax highlighting, okay, on, you can see, to do is highlighted. Okay, just because a lot of people use the word to do to remember, important parts of their, programs. But this really kind of makes it kind of hard to read the rest, so I have to turn off syntax highlighting. Are we still doing okay so far with this program? So I'm stopping right now just to make sure that I'm using the diff-out instruction correctly. Okay, so get it off, assemble, link. But this time I have to use a GDB because otherwise, the program is not going to stop. Well, actually it does stop, but it won't do everything correctly. So I'll use GDB anyway. And GDB, I will put a breakpoint at line 36, right before it's doing the division. And I also have to change the program so it is going to EAX, it's not going to be 0. So let's go back to the first part of the program. Put a breakpoint at print hex itself, so I can change EAX, right at the entry point of the subroutine. Run the program, and this time I want to set EAX to be a different value. If I remember correctly, I can use a set variables %EAX equal to something to change the value of the register itself. So let's give that a try. Let's try 18. So with 18, no symbol variables, cool, singular, okay. And then I can use an IR EAX just to make sure that EAX is in fact, changed in this case. Are we still doing okay so far? Is everybody still kind of following what I'm doing with the debugger in this case? Okay. So this is a great debugging tool because what you can do is you can set a breakpoint at a certain point of your program. So even though the rest of your program may not be correct, a certain register may have the wrong value at that point, you can always inject the correct value so you can debug the rest of the program, assuming the input is correct for that particular, at that particular point of execution. Okay, so now we can just go ahead and continue at full speed. And we are now at the first instruction for the division. So I'm single stepping through this one. I just want to double check EDX should be 0, EAX should be 18, the number that is being divided, and then EBX should be 16, which is the divisor, EBX here. Okay, single step one more time, and now I should have the remainder in EDX. So EDX should be 2, and I should have the quotient in EAX, which should be 1. And so I have just verified that my understanding of how the division instruction works is okay, is correct. Okay, because I would not continue to write programs making the assumption and think, okay, I must be using the division instruction correctly, because that would, if I actually made a mistake somewhere, that would just kind of push the bug down and makes it kind of hard to debug. So that's why I would test the program even though it is incomplete. I would still test it at this point. If I have been using get, I would probably check it in at this point, just so that I know the program is working fine and I can verify up to this point. How many people are starting to use a get or some sort of a revision control? Very few. Okay.
Save multiple copies.
Huh?
I just saved a bunch of
Save multiple copies work too. You can also send it to you yourself by email. So that automatically has a timestamp to it.
timestamps in what I save.
And if you do it by Gmail, you also have a very reliable way of backing up everything. Because chances are, if Gmail goes down and they lose all the messages, you may be in trouble because you cannot turn in your homework. But a lot of people will be in bigger trouble too. So that's a good way to back up your stuff. All right. So now let's go back and continue to finish this program. All right, so what I'm doing now is, okay, the first thing is I can remove that. All right, so at this point I can, the first thing I want to do is to say, well, do we need to save EAX ahead of time because it seems like EAX is important? Well, let's take a look here. What are we doing to EAX? EAX is n, but in order to prepare ourselves for the next subroutine call, we have to calculate n divided by 16 anyway. So EAX is already set up, to that point of the execution. So I don't really have to save EAX before the division instruction because, after the division instruction, EAX is just what I want to be, in there because it is the quotient of n divided by 16. Okay. So here I have to compare. Okay, let me just change this one at a time. So in order to implement this, I can say, if CH is greater than or equal to 10, go to, now this part you have to be careful because we are already in the else branch, so you don't want to say else. So in this case, I will just say, else, because it is the else of a conditional statement in the else branch already, in the outer else branch. Okay. So if you stack things up like this in a systematic way, you cannot, you reuse the same label. Okay, it's just not possible. And then the else label will be defined here, else. And we also have to remember in the then branch at the end, we have to do an unconditional branch to the end of this particular conditional statement. So this is already inside another conditional statement. So I would say else and if, because it is the conditional statement inside the else branch of the outer conditional statement. And we'll call it 1 because there's a second one. So else and if 1. You can see that else is a prefix for everything that I use inside the nested part of the branch. Okay, any questions at this point? Now you obviously do not have to choose the label name exactly the same way that I do, but you have to come up with a systematic way to do it. Okay, whatever you do, it has to be systematic so that you don't accidentally reuse the same label name again. Okay. At this point, I think I'm ready for assembly instructions. So we can just do a compared instruction of some kind, condition, and then we have a conditional branch to else. Okay.
Somewhat off topic, but what characters can I use within label names?
Sorry?
What characters can I use within label names?
I believe you can use a dot. The period can also be used.
Or a dash?
Dash, I don't think so. Underscore, you can.
Underscore.
Yeah, underscore is okay. So basically anything you can do in a C identifier, you can also use as a part of a label name. Plus the dot symbol can also be used. I would not use it yet just because of habits. Not using it. Okay. All right. So the question now is how do we fill in the details? We are comparing 10 to CH. Now in this case, you do have a choice of whether you want to do a compare long or compare byte, because EDX is the remainder of a division by 16. So that means whatever it is, the value has to be fit. It will fit in a byte as well. Because when you're looking at the remainder of after division by 16, what can possibly be the value of that remainder? It can go from 0 to 15. Okay. So we know for sure in this case that it will fit in a byte. So if you use a compare byte in this case, it will work just fine. But I can also use compare long because the entire register EDX is the remainder of the division. So in this case, you do have a choice. It doesn't matter which one you pick. Neither one is faster than the other one. Whether you're comparing a single byte or comparing 32-bit, since the architecture itself is 32-bit to begin with, it will still take one cycle to complete the operation. So in this case, it doesn't really matter which one you pick. You just choose one and be done with it. And the comparison is saying that if we confirm that the relationship is greater than or equal to, so that's basically not less than, but since this is also unsigned, you have to use J and B for not below, because it is unsigned. Okay. Do we have any questions at this point? No questions? This is all okay? Okay. If there are no questions, what we'll do is we'll implement this particular instruction here. Once again, CH is actually our EDX at this point. It's a 32-bit register. So whether you want to use an add long or add byte or add word doesn't really make a whole lot of difference. So since I'm using EDX, I'm going to use add long. So $, the ASCII code of 0, to EDX in this case. All right, so I have just finished the else branch, the first part of the else branch here. I can go ahead and do this part too because it's really kind of similar to the other one. So let me just kind of go ahead and finish this one. So we can just say add long $, in this case quote a quote, which is the ASCII code of lowercase a minus 10. That is perfectly fine. Because the only thing you cannot do when you have an expression after the $sign is when you have a reference to a memory location. That would not be okay because it's no longer an immediate operand. It cannot be an immediate operand. Or if you refer to a register. And because a register also has a runtime value, you cannot refer to the runtime value in an immediate operand. But as long as this is a constant that can be resolved by the linker, it's fine. This is actually resolved by the assembler. Because the ASCII code of lowercase a is already known to the assembler. And 10 obviously is just a literal constant. So there's no problem with this expression after the $sign. And we are also adding this to EDX. So now we are done with the first conditional statement in the else branch of the outer conditional statement. Are we okay so far? I'm not too concerned about the recursive call here. Let me just finish up the write operation just to make sure that I'm converting the values correctly. So I'm writing the program in a kind of weird way because I'm not finishing the entire program all at once. So I should probably leave a note to myself here to do, implement the recursive call. Okay. So this is a reminder to myself that I need to finish that. And then we have the same write operation here. This time is a little bit tricky because we have EAX is set up correctly. We don't really need that anymore, but we can always push and pop it to restore that. We have EDX being or DL being the character that we want to print. Okay. But EDX is also used as a parameter to the system call. So I have to make sure that I utilize the character to be printed before it is destroyed, so that it becomes the count, the number of bytes to print for system surface number 4. So here we have push L EAX and then followed by pop L EAX. And this is the usual way that I do things. It's just like opening and closing the braces and then fill in stuff in the middle. So this way, I know that in between it's now safe to modify EAX. So move long 4 to EAX because I want to do a system write. EBX is not used anywhere. It was used as the divisor, but since it's reinitialized every single time, it's okay. I don't have to save it here. So that would be the file handle. Now, 1 is the file handle of standard out. ECX is the location where I'm printing. So right here at this point, I have to do a push W or push L instruction with EDX. So in this case, it's just DX here. Because DX, okay, this is a little tricky. DX contains the character that I want to print. Okay. And after the push L instruction, I would do a move L %ESP to ECX. Because ECX, register ECX is supposed to contain the address to the byte that I'm supposed to print. And because I just pushed that byte on the stack pointer is now pointing to exactly that 1 byte that I want to print to standard out. Basically the same thing as last time, except this time I had the character to be printed is no longer just 0, it is now in register DX. Are we still doing okay so far? Okay. And then we have only one more register to initialize, which is EDX, which is the number of bytes that we are printing. It is just 1. I'm just translating everything from the C code here. Okay. And after obviously I have to remember to do the actual software interrupt. After the software interrupt, I will still have the 2 extra bytes that we push on the stack using the push W instruction, just like last time. I have no use of those 2 bytes anymore. So adding 2 to the stack pointer will deallocate that. So I think I'm ready to test this code, just to see whether it is working up to this point or not. Reassemble, link, GDB, and this time I want to definitely set up a breakpoint. Oops, b print hex. Okay, so when I've run it the first time, I will set variable EAX to well, let's test it from 0 to 9 first. Okay, so I put let's say 7 into EAX. The program should print the ASCII code of 7 in this case. Okay, the recursive portion is not working, so it can only print a single digit at this point. Continue execution, and we have a 7. So it's working up to this point. Let's check values that are from 10 to 15, so it can print A to F as a lowercase letter. So run the program again. Once again, we set the variable to, let's say, 12. So with 12, it should print C. Lowercase c represents 12. Continue execution, and it does print the C here. So at this point, I know the main part of the logic is already correct. Now I can just focus on when do I need to do the recursion. Are we still doing okay so far with this program? The details, you can always just kind of re-watch the video, or I can just upload the file. So don't worry about the actual detail of the program. It's more like the process that is important, and also the concept that we are using in this program that is important at this point. So are we still doing okay in terms of the main concepts, and also kind of the approach, the process that I'm using to convert the program? Is that still okay? All right. So now I can get out from GDB and back into the source code to finish the last part of this code, which is really just the recursion control here. So get rid of the to do, because I'm just going to do it now. So I can say if n divided by 16 is 0, go to else and if 2, because this is the second conditional statement in the else branch. And that label will go be here, else and if 2 is going to be defined here. This is one thing that I find to be quite useful, is when I refer to a label the first time, I will also define the actual label at the right place. So that way I don't have to hunt for the right place to put that label. When the assembler complains, hey, you're jumping to a particular label, but you never tell me where the label is, at that point I would have lost my train of thought already, and then I have to really read the program in detail just to find out where I was supposed to put that label. So I would always do the go to or the jump and then the label right away, just so that I don't lose track of where I'm supposed to go to. Well, it looks like we can do this part pretty easily, because n divided by 16 is already stored in one register. Which register is storing that quotient? EAX. Yep. Okay. So we compare long 0 to EAX, and we just need to confirm that it is 0 in order to go to else and if 2. So JZ will work just fine to else and if 2. So that will finish up the conditional branch. And inside here, that's actually super duper easy, because the parameter n divided by 16 is in EAX already. So that's just kind of handy. I did not actually plan it out this way. It just kind of works out. So because it's already in EAX, I don't really have to do any type of computation. I just have to call recursive print, or in this case print hex by itself. Call print hex. That's all I have to do. So I think this program is done. Okay, so we'll go ahead and test the program. Reassemble, link, GDB. We'll put a breakpoint at print hex so that we can just inject a different value into EAX every single time. Now, when you're testing a program after making so many changes, it still makes sense to print 0. Okay, in other words, you want to do a regressive test of your program, meaning that all the previous test cases that was important at one point, you still want to keep those test cases, okay? Because they are still important. You want to make sure that none of the new code is corrupting or messing up the program. So something that used to work is now not working. So we'll So go ahead and run the program. And EAX is 0 to begin with, IREAX. So we'll just go ahead and continue. It still does it prints 0 correctly, okay, just like before. That's good. Now we can do the regressive test on 7. So we set var $EAX to 7. Continue execution. It prints a single digit of 7 correctly. That's good. We can try run it first, and then set the variable to 12. Okay, so it should print C in this case. That part is still working. So everything that was tested before is still working. So now we can try something that is a little bit different, maybe 2 digits. Okay, maybe just AB. It should print AB in this case. Oh, haven't started to run yet. Okay, so set var, continue execution. And this is good, okay? It's not printing AB because it is a recursion, okay? Because it's 2 digits, it needs to call itself 1 more time. So this is actually right on the money, okay? The program is doing everything that I can, expect it to do right now. So if I continue at this point, it should print, the digits. Ooh, okay, so it prints A correctly, but B is not done correctly. But that's because, what is it supposed to print? Okay, let's go back to the code here. Okay, so let's quit. Okay, there we go. Okay, so if you look at this program, what it's supposed to print here is, not this one. Oh, it is correct. Okay, this is the right point. It's supposed to print something in DX. Do you think print hex is going to mess with DX or EDX? Yeah. So that's why it is also important to preserve DX across the subroutine call. Okay, because DX is important to me, and that's why when it's calling print hex, I'll just go ahead and save it first, push EDX, and when it returns, do a pop EDX. Because print hex is going to change EDX, and I know that I need to rely on the value of DX for an operation that is after the function call. So that's why it is important to preserve the value of EDX. But you can tell, this bug was easy to pinpoint because it didn't have any problem when it was a single digit. When it was a double digit, the first one was printed correctly. It's the second one that did not get printed correctly. So that everything points to the fact that the register is just corrupted when we return from the subroutine. Okay. Are there any questions about everything that I just talked about? Yep, go ahead.
Instead of call for text, couldn't you do a go-to for text and still have that?
No, definitely not, because we have stuff to do after we come back from print text. It's not a tail-end recursion. When you have what we call a tail-end recursion, which means the recursion is the very, very last thing to do, yes, you can turn it into a go-to. Basically, you're turning the whole thing into a loop instead of a subroutine call. But in this case, we are explicitly waiting for the subroutine to come back so I can finish up the very last operation, and therefore we cannot just do a go-to, because if you just do a go-to, it becomes an infinite loop and just not come back. Or it will do all the recursion, and then at the very last recursion, it will do a return, and it won't print anything. Or it will just print a 0, or the least significant digit will be printed, nothing else will be printed. Okay, so let's test the program again. Assemble, link, GDB again. Put a breakpoint at print hex. Run the program again. And this time I'm just kind of concerned about the one thing that I was trying to fix. So set var EAX to AB. Continue execution at full speed. And then continue again. This time it does print AB, so that's the correct output. The program is now, verified as much as I can in this case. Okay, any questions about this whole thing? Now, this program only utilized the concepts that we have talked about up to this point. Okay, using registers, to pass as parameters, calling, returning, push, pop, system calls, conditional branches, and comparison. And the division instruction is the only one that is new to this program. Any questions? Any questions? Okay. So at this point, we are basically saying it is okay to pass parameters using registers, but it has a very big limitation, which means we only have so many registers. If you have more than let's say 8 parameters to pass, then you'll be running out of registers entirely. Okay, which is not a good thing. Okay, C subroutines, generally speaking, have no limitations of the number in terms of the number of arguments or parameters. Okay. So the next question is, how are we going to solve this problem? How do we pass information to a subroutine so that it is, one, not a global variable, and two, it is not a register? We use the stack, exactly. So the call frame is all about the stack. How do we use the stack to do this, to do that, and to do everything? Because potentially at this point we don't need global variables anymore. Okay, so let's go ahead and let me go back to the notes that we were at earlier. All right, so we are now officially starting to talk about the call frame, and this is the notes, or a link to a portion of the book that I was writing for this class that talks about the call frame. Passing parameters through the stack is something that we're going to do now. Okay. Before we move on, are there any other questions? No other questions? Okay. Now, before we get started here, what we'll do is we'll write a C program, plain C program that has a parameter, and then we'll take a look at the address of the parameters so that we can see, is there any relationship between a local, not a local variable, but a parameter and a stack. Okay, so that's the first thing we'll do. So switch back to the text screen here. I can teach this whole class out of SSH. All right, so let's go to today's class. Okay, CISP 2013-0411, cisp310. Sorry. Maybe I didn't create it. Okay. Here we go. So now we'll go ahead and write a very simple program here. Okay, address of parameter. That's the name. So void f. We'll just have a single parameter here. Well, let's have 2, okay, so that we can actually compare the addresses of the 2 parameters. Doesn't do anything here. Okay. Hopefully the compiler is not smart enough to optimize this whole thing out. And we'll just call f with 2 particular numbers, 45 and 78. Okay. So this is an entirely useless program, other than the fact that we want to, look at the address of parameter n and parameter m in the subroutine. So I just need to make sure that there's a way for me to specify a breakpoint here. Let's keep it this way and see whether we can do it. GCC-O address of parameter -G to include debug information, and then the source code, the name of the source code. Okay, compiles without a problem. GDB address of param. Put a breakpoint at line 2, okay, if possible. Run the program, and it is setting a breakpoint at line 4, which is okay because line 2 and line 4 are logically the same since I have nothing in between the curly braces. So at this point, it does tell me that n has 45 and m has 78, but that's not what I'm looking for. What I'm really looking for is the address of those two parameters. Okay, %n has an address of BFFF A30, and the address of m has a mixed address. Okay, so n has a lower address, m has a higher address. But I also want to find out, whether this is just somewhere really out there, or is this even close to the stack pointer? Okay, so I want to take a look at the stack pointer, and the stack pointer is pretty close. Okay, so we have a suspicion at this point. We have a suspicion that the parameters are also pushed on the stack. Okay, because you can look at the addresses and you can see that they're pretty close. They're too close to be random. Okay. In fact, if you look at the address of n, it's really just 8 bytes out of where the stack pointer is currently pointing at. Okay, which is not a whole lot. Now, what you can also do is you can write another subroutine called G, and you pass n and m to G, and you see whether the address of n and m kind of floats with the stack pointer. Okay, because if the stack pointer and the parameters are not in a floating relationship, or the displacement are constant, then you can say that, well, maybe it has nothing to do with the stack. But if the displacement between where the stack pointer is pointing at and the address of your parameters, if they stay the same regardless of where the call is located, then you have good reasons to suspect that this is stack-based. Okay? The other question that we might have at this point is, what are those 8 bytes between where the stack pointer is pointing at and the first parameter, which is n? Because we do have 8 bytes that are quote-unquote unaccounted for. What we can also do is to take a look on the stack. Just because you're writing or debugging your program as a C program doesn't mean that you lose the ability to do memory dump. So we can still do memory dump in this case. So we'll do a memory dump, 2 things. Each one is a 32-bit thing in hexadecimal. And we'll dump from wherever the stack pointer is pointing at this point. Okay, so we have these 2 bytes here. This is the one that has the lower address, and this is the one that has a higher address. That thing looks kind of familiar in a way. The one that is highlighted right now. It looks like an address of the space where we can store programs, because when we run programs, it seems to be in that particular region. Okay? But you can confirm that pretty easily, because what you can do is to print the address of main. Okay? So you can see the address of main is at this address, and this address that is stored on the stack for whatever purpose it is closely related to the address of main. In fact, this is main. It ends with E1. This is the address on the stack. It ends with FB. They're pretty close. Okay, they're fairly close. So at this point we don't know what it is, but we have a kind of general idea of hey, it is some location back in the main function. All right, so we have all these observations and kind of suspicions, stuff like that. So the next thing we want to do is to figure out how is it doing this, okay? Or why are we doing something like this? But let's deal with the why first. If I push, or if I use the stack to pass parameters, do I have a practical limitation of how many things or how many parameters I can push on the stack? No, because the stack is pretty big. There is an actual limit to it, but practically most of the time we don't really get close to hitting that limit. The second thing is, are we still relying on any type of global variables to push things on the stack? Or, okay, I just said something that is self-contradictory. Are we still allocating some space out of the global region of .NET? No. If I push everything on the stack for parameters, then I'm not using .int or anything like that to allocate memory, which is a good thing. Okay. Okay, so let's go ahead and check out how we can confirm some observations here. Okay. So what I'll do next is I'm going to write a subroutine in assembly and call that subroutine from C, so that I can just kind of observe, is that the right thing of interpreting the stuff on the stack? Are we still doing okay so far? Okay. So I'm looking at this program here and say, okay, I'm going to write the subroutine f in assembly. So I'll just go ahead and comment out this entire definition. That's a really interesting way, but it's a very good way to comment out an entire subroutine, because pound if 0, and pound and if, they can be nested. Unlike slash star and star slash, which cannot be nested. This can be nested because it is it's done by the preprocessor. Okay. You can also turn that pound 0, pound if 0. You can change the 0 into a macro, so this way you can control the behavior of the compilation using macros, which can be very handy. You do need a prototype, to make the C compiler happy, which is really just saying, we have an N and we have an M, with as parameters. Okay, so the C compiler will be happy just having this. Okay, so we'll just go ahead and do a GCC, but this time we'll do a -C to compile just to the object code, but not the executable. And then we have a -G address of param.c. And when you do a ls, you can see that we have a .o file as the output, which is the object file. Now we'll write function f in assembly. So we'll write function f in assembly using f.s. So f.s, which is based on the name of the subroutine. So in this case, we have .text, .global f, because f has to be exported so that the linker can see it. And this is the entry point of f. Okay, f is going to return without doing anything. Okay, but we want to double check and see what is on the stack and why do we see all those other things on the stack at this point. Are we still doing okay so far at this point? I'm just setting this up so I have a place in assembly so I can kind of catch it and say, since I'm not doing anything inside the subroutine, what is set up by the caller from C? Are we still doing okay so far? Okay. So it's kind of like investigation, investigative work here. Okay, so now I have to do the assemble of this program, of the subroutine itself. AS, G stabs, -O, F.O, F.S. So now when you look at the files that we have at this point, we have the object file of the C code, we have the object file of the assembly code. What is left to do is to link these two. And I'll use GCC to do the linking. GCC-O address of param, and then we have address of param.O and F.O as the input to the linker. And everything links just fine. We now have a final executable called address.param. Okay, when you run the program by itself, obviously it doesn't do anything. But if you GDB the same program, then we can start to do something. Okay, because what I can do is I can put a breakpoint in the assembly code. So I can list f.s, not defined. Okay, :1. There we go. When you want to look at the listing of a file that is not the current file, you can always mention the name of the file and then with a line number after that. So in this case, it's in f.s, and I'm starting with line 1. I want to put the breakpoint on line 4 of f.s, just so that before the return statement, I have a chance to look at the entire stack and see what is on the stack at that point. So I will put a breakpoint on line 4 of f.s. This is the way to do it. You specify the file name first, colon, and then a line number where you want to put a breakpoint. And then I just run the program at full speed. Now we're at the return statement. Now this subroutine is written entirely in assembly, which means I intentionally did not put any instruction in the subroutine. So everything that I see on the stack, they have to be done by the caller. Okay? It has to be done by the caller because the subroutine itself is not doing a single thing. So the first thing is I want to look at the stack pointer. Okay, it's someplace, but that doesn't seem particularly interesting to me. So the next thing I want to do is to look at a few items on the stack. Let's look at 4 items on the stack. Okay. In hexadecimal, starting at wherever the stack pointer points to. And we are seeing these 4 things on the stack. What do you think is the leftmost item that we're displaying here? Remember, we are ready for the return statement. So whatever the stack point is pointing at has to be
Wherever we're returning to.
wherever we are returning to, which is also known as the return address. Okay? Okay, that's the return accuracy. 2D and 4E, I don't remember those things. Oh, but they're in hexadecimal. Okay, 2D in hexadecimal is what in decimal? Is 2 times 16 plus 13. 45. Okay, I vaguely remember a 45 in the program. That's n. Okay. What about 4E? 4E in hexadecimal is 4 times 16 plus 14 in decimal. 78. All right. So those things seem to be actually on the stack. So we have the return address, and then we have n, and then we have m. Are we still doing okay so far? The next question now is, can we access those two parameters from inside subroutine f? Yeah, we can. We can definitely do that. Sorry?
Move the stack pointer.
Well, one way is to move the stack pointer, but we have a very convenient addressing mode that will let us access stuff that is close to where the stack pointer is pointing at. Does anyone still remember the addressing mode? This is exactly. Oh, I'm impressed. I am impressed. It's the base addressing mode. Okay. So what we'll do now is, now that we know how things are kind of structured. Okay. Now I do have to point out one thing that is kind of important. The first parameter has a lower address, and then the second parameter has a higher address. Okay. Now that is important. How many people know that in C, but not necessarily in C++, I think the feature is in C++ as well, you can actually define a prototype that looks like this. Okay, let me just put this first, go back to address of param.c, and I'll just call this funny. And funny has an integer n and this. How many people know that you can have a ... as a part of the parameters? Okay. Okay. Have you used it? No. Okay. The ... means you can have any number of parameters after n. In other words, the compiler will only enforce that when you call funny, you have to supply an integer. But after the integer, you can have anything and any number of anything. So you can have pointers, you can have void pointers, char pointers, more integers, floats, doubles, address of ends, blah, 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 blah. It doesn't matter. Okay? And that's really important because in order to implement something like this, that means I need a way to find the address of n, and then from the address of n, I can try to figure out what else should be there on the stack. Okay? And that is driving the fact that n has an address that's lower than m. Because if it's reversed, then we won't be able to find the first parameter. Okay. All right. So what we'll do now is, this program is the main program is just the way it is. But what we want to do in assembly.
How would you actually get to that random stuff?
What?
How would you actually reference that random stuff?
How do you get to the random stuff?
Yeah, in C.
In C? Oh, okay. Well, let's talk about that. Okay, sum n dot. Okay, so what I want to do is to implement sum so that n is the number of things that I'm supposed to add. And those are supposed to be supplied by the dots. Okay, so in the main program, when I call that, I can call it, and utilize the result. Okay, just have a local variable x here, x equals sum, and I have to specify how many things first. So let's say I have, let's say 3 things, and those values can now be whatever they are. Yep, those are 3 already. So that's one way to use the dot.
No, but I mean, once you're actually in the.
Oh, when you're in the subroutine?
Yeah, you like n plus 1.
Okay,
And
well,
then
let's go ahead and do that too. Okay, so the first thing you need to do is to have a pointer to point to the very first one that you're expecting. Okay, so in this case, we'll say p, which stands for pointer to a number. Okay, the way this is going to be initialized is we'll refer to the address of n as our anchor because that's the only one we know, but everything is after that, right? So we'll just say that, we'll start with that, but we know the one that is after this is going to be +1. But since this is in C, the +1 is typed, which means we're adding the number of bytes used by a int pointer itself.
Okay, gotcha.
Okay? So that would be the first one.
Okay.
And then the rest of the code is really just, I need a sum to store the actual sum so I can return that.
Yeah.
And then we can say while n minus minus, yeah, that'll do it.
Okay.
And we can say sum plus equal to dereference p num plus plus, and return sum at the end. Okay. How many people know what that code means? It's in regular C. There's nothing that's tricky about it. But I just wanted to make sure that you guys still remember all the stuff about addresses and incrementing and stuff like that in C and C++. You can do that in C++ too. I'll just kind of go over that because I think it's important that you guys know how to do it.
So we could do based index in C if we wanted.
Hmm?
We could implement a version of based index in C if we wanted. It'd just be really weird.
Yeah, kind of.
That could be weird.
Okay, one thing that you have to remember is the precedence of operators for this guy here. Let me just kind of highlight the portion I'm looking at. This portion here. Without knowing it, if you are not sure about the priority of operators, you should use explicit parentheses to make sure that this is evaluated in the right order. Because you can look at it two ways. You can say, am I post-incrementing whatever p num points to, or am I post-incrementing p num and then dereference whatever it was pointing at before the increment. So those are the two possible interpretations of this if you do not know the precedence. If you know the precedence, then you know that the actual right interpretation of this is it's the same as putting parentheses around the plus plus. So basically you're doing the post increment of the pointer itself first, and then you dereference the address before the increment. Okay? And this is why people do not like C, because you can have a single statement that appears on one single line that is doing really a lot of things in a cryptic way. But it is really just kind of handy. Okay, it's handy on one side, on one hand, and it's also kind of obscure on the other hand. Okay. Are we still doing okay so far? Okay. So getting back to assembly programming, we have 5 more minutes to talk about that. So in f.s, we'll just kind of stop at this point. Right after this, we'll take a stop, and then on next Tuesday we'll have the practice exam. So we won't come back to this stuff until the Tuesday, until the Thursday, next Thursday, 1 week from today. Okay, so what I'll do now is I will define some labels. Okay, so the first thing I'll define is the return address, and I will define it to be 0. Well, are we returning to 0? No. This label has a special meaning. Return address is the number of bytes as an offset from where ESP points to the actual return address. In other words, everything is now defined as an offset from ESP, or where ESP points to. If I know that return address is quote unquote 0, then the parameter n, which is our first parameter, is going to be the return address plus 4. Okay, so in this case, n is the number of bytes from the number of, okay, it's the offset. Okay, offset of parameter n from where ESP points to. And then the same thing, for the same reason, m is n plus 4, because n itself is 4 bytes, and that's why the offset to m is n plus 4. Are we doing okay so far with these definitions? Yep, go ahead.
So the first thing off the stack is the return
if I were to pop, yes, the first thing that you're popping would be the return address. And that's why I don't want to pop. That's not, I want to be able to access the parameters, but without having to pop anything from the stack. So what I'll do here instead is, now EAX is a register that is free for any subroutine to use, so I don't have to preserve EAX. So if I want to do any type of calculations, I can do this. I can basically say move L N ESP to EAX. So the comment of this is EAX is now the value of parameter n. Is that okay? The first operand of the move L instruction is the base addressing mode. In other words, I'm almost accessing whatever ESP points to, but not quite, because I've added n as an offset to the indirect operand. And that turns out to be, it's on the stack, and that turns out to be our parameter n. I'm moving into EAX. If I want to add the two numbers, the next instruction is just, add L, M, ESP to EAX. So this will make EAX the sum of the two parameters passed to the subroutine. Are we still doing okay so far? Okay. Let's go ahead and test this theory, okay? And then the third thing we also have to understand is EAX is our return value. In C, in GCC, EAX is the register to store a return value when it is a scalar. Okay, that's just by convention. Yep.
I'm having trouble seeing what return address setting to 0 does, when you could have just said n equals 4 and m equals n plus 4.
You can say n equals to 0 plus 4, which is 4. But I want every single item on the stack to have a label. Okay. That's why I have a return address. Because later on we'll see that there's one more thing that we have to put on the stack that is below the return address. So that one would have a different label. Okay, so these numbers will change but after we talk about the frame pointer. All of these things will be off by 4 bytes. Okay, but I do want to have a label for everything that is on the stack right now. Okay. All right. So let's test this code and let's see whether it works. Okay. So to test this code, we have to go back to the original C program. I don't really need to test this part here, so I'm just going to comment out this part. Oh, okay, maybe leave this part alone, and then make that. Oh, I have to change the prototype so that f would actually calculate the sum of the two parameters. So let's go to this part here, change the return type of f to an integer instead of void. Otherwise, the compiler would not let me do this. Okay, and we'll just go ahead and recompile this the C code first. So we compile the C code into an object file, reassemble the assembly code, and then link the two together. So we have address like that, and then f.o is the other one, gdb address.param. And we just want to put a breakpoint on line 25. Well, we can actually put a breakpoint on the subroutine itself, and then we'll put a breakpoint on line 25. Okay, so we'll just run it at full speed. Now it's stopping on line 25. Continue. It is now stopping inside the subroutine. So we single step through this instruction. Look at EAX. It is 45. In other words, we did move the first parameter into EAX, because it is very unlikely that we find another 4 bytes that is representing 45 on the stack at this point. We single step the second instruction. That should have added 78 to 45. So if you look at EAX, it is 123, which is 45 plus 78. So the next question is EAX really used to pass the return value back into C? That's the next question. So single step, now we are back into the C code. The assignment operation is done because we are ready to execute the return statement in C. So we can do a print x in C and see that x actually has the value of 123. So what we have demonstrated up to this point is a few standards used by GCC, basically to allow a subroutine to communicate with whatever code that is invoking or calling it. Okay, the placement of the parameters, as well as the fact that we are using EAX to return a scalar value. What if you're returning a whole structure? Well, that's actually a little bit more complicated. We'll deal with that later. But in C, you can actually return an entire structure. Did you guys know that? Okay. It's rarely used, but it is possible. But for any scalar, returning a char, a short, an int, you use EAX. I suspect returning a long is using EDX and EAX, which is the tradition used by Intel. All right. So are we good so far? Okay. So you still have your homework assignment that is due on Tuesday, and then we have the practice exam on Tuesday as well. So we'll be ready by Tuesday. Question?